Section 8.3, Inverse Trigonometric Functions. We want to be able to solve trig equations. That is going to make graphing functions a lot easier. It'll make it easier to find x-intercepts, vertical asymptotes, stuff like that, like we were trying to do in the previous section. In order to do that, we need to know about inverse trig functions. So that's what we're going to explore in this section. Recall from your college algebra class, or even before that, when you first start thinking about functions, we'll draw a lot of different types of diagrams. One type of diagram that we draw pretty often is this one. And we think of a function f as being this kind of machine that takes some input x, and it does something to that input value, and out comes f of x, or f applied to x. Okay, so we interpret the function as this machine that receives inputs, modifies them maybe, and then outputs something on the other side, which we call f of x. Okay, recall that we can actually take this machine and put it in reverse, but it's going to change what we call this machine. If we change the direction, if we change the direction of this machine, we're going to call it f inverse. Okay, and we're going to be putting in values of y. So these are like what used to be the output of the function. And then out is going to come f inverse of y. Okay, so what this function is going to do is it's going to do the opposite of whatever f did. So if f adds 1 to every input value, and that's how you get the output, f inverse is going to subtract 1 from every input value, and that's how you'll get the output. Okay, another drawing that I think is really helpful is thinking about domains and ranges. So let's say that we have some function, and here's the domain of f. And over here we'll have another set, which is called the range of f. And what the function f does is it takes values that are in the domain. So like, let's say we have a little x value over here. And then we have over here in the range just some y value. What f does is it carries x over to this associated y value in the range. Okay, so that is what the function f does. Now, how is the inverse function f inverse going to fit into this picture? Well, remember, f inverse just takes whatever the y value is and sends it back to the original x value. Okay? So f and f inverse kind of undo each other, right? Like if we're looking at the composition f of f inverse, that just sort of takes one of these values, you know, like the x value, and sends it over to y, and then sends it back to itself, back to x. Okay, so that's just a very quick and general reminder of what inverse functions do and how they work. Okay, so that's what we're talking about over here on the left, some properties of inverse functions. The domain of f inverse is the range of f, right? Because if f inverse, that's our green function down here, the domain is the values that go in to the function f inverse, right? And notice that our inputs come from the range of f. Okay, and similarly, the range of f inverse is the domain of f. Right? Where are these y values getting sent to? Well, they're getting sent over here to what was originally the domain of our function f. Okay, and then y equals f of x is equivalent to x equals f inverse of y. That's kind of what we're discussing up here with this machine diagram. The graphs of f and f inverse are reflections of each other over the line y equals x. A little example of this is the square root function. Looks like this, right? That's y equals the square root of x. And the inverse of the square root function is actually just the right half of the graph y equals x squared. Notice that these two graphs are just reflections of each other over that diagonal line y equals x. Okay, this will be true for any pair of functions that are inverses of each other. Okay, and the last two properties are kind of come together. F of f inverse of x is just equal to x. So if we compose f and f inverse, it's going to act like the identity function. Okay, the same thing will happen if we do f inverse of f of x. And I just kind of think about this picture, right? Like if we're looking at f of f inverse of x, so there's f of x, and then there's f inverse of that output. Notice that it just brings us right back to where we started, x. Okay, so just a few properties about inverse functions. Let's start looking at some trig functions now. Okay, so recall that sine of x has a range from -1 to +1. And since sine of x is not 1-to-1, we'll need to restrict the domain to create an inverse. So remember a second ago I mentioned this relationship between y equals square root of x and y equals x squared. And I said that the inverse of y equals square root of x is just, the right half of y equals x squared. Why is this? Well, notice that if I included this left branch of the graph of y equals x squared, what happens when I reflect that over the that line y equals x? Well, I end up with this down here, right? This branch would also be included in this graph of y equals the square root of x. And why is this a problem? Well, remember we have this thing called the vertical line test. If I draw a vertical line, if this graph intersects any vertical line at more than one point, it means that it's not a function. So notice that this graph, this sideways parabola, it doesn't pass the vertical line test, therefore it's not a function. Therefore, it can't be an inverse function. So at times we have to do this tricky thing where we restrict the domain of the starting function, x squared in this case, to make it 1-to-1, meaning it'll pass the horizontal line test. Okay, so all things that we talk about in college algebra. So we want to do something similar for sine of x, because notice this is not 1-to-1. If I draw a horizontal line, it's going to intersect it at infinitely many points, right? In order to have an inverse of a function, we can only have any vertical line, any horizontal line intersecting at 1 point maximum. So how do we want to restrict the domain of sine so that it is 1-to-1 and then we can create an inverse? Well, I want to be sure to include every value in the range of sine. I don't want to be too restrictive. A good way to do it is let's just pick one trough and one peak, right? And just restrict the domain between those two values. So if we restricted the domain, in this case, between -pi/2 and pi/2, this might be a good choice because, we're going to include that entire range from -1 to +1. Okay, and we're not going to violate the, this being a 1-to-1 function. If I go any farther, notice that then it's not going to pass the horizontal line test. So I don't want to go any farther than just that little section right there. Okay, so we're going to restrict the domain. Let me write this. I'll say we will restrict the domain of y equals sine of x to this set from negative pi over 2 to positive pi over 2. And I'll use brackets there because we'll include those endpoints in that domain. Okay, and now that we have, a sine function which is 1 to 1, we can reflect this over the line y equals x, and we'll get a graph and define this function y equals sine inverse of x. So there's our notation. This is sine inverse. Or sometimes we write arc sine. This means the exact same thing. So if you see arc sine or sine inverse with a little, negative first power, kind of following the standard notation we use for inverses, those both mean sine inverse. And the inverse function is going to have a domain of -1 to 1, because remember, the domain of the inverse will be the range of the original function, sine of x, and the range is going to be negative pi over 2 to pi over 2, which is that restricted domain of the sine function. All right, and we do that reflection and we get this graph right here. So this is what arc sine of x, or sine inverse of x, is going to look like. Okay, and we'll have some ordered pairs on here that will be sort of familiar, like, okay, like this ordered pair right here. Let's see, I think it's about right there. This is the ordered pair root 2 over 2 pi over 4. Let's be a little more accurate here. Okay, so you might recognize that, sine of pi over 4 is equal to root 2 over 2. You probably have that memorized from the first quadrant of the unit circle, or from, dealing with right triangles. So that means that sine inverse of root 2 over 2 is going to be equal to pi over 4. Right? So that is why we have that ordered pair root 2 over 2 pi over 4 on the graph of y equals arc sine of x. Okay, and then here's just another sort of formal definition of y equals arc sine of x. But we already kind of talked about that. There's the domain and the range and all that. So now we want to start working on evaluating inverse trig functions. So let's deal with, example 1. We want to find the inverse sine function evaluated at root 3 over 2, negative root 3 over 2, and -1. We're going to develop a little strategy for doing this. So the first thing to note is, remember, when we're dealing with a sine function, or any trig function for that matter, the input is going to be an angle, right? And we'll either get it in terms of degrees or in terms of radians. Now, for inverse trig functions, the output is going to be an angle. So the way I like to start these is I like to say, let's let theta equal arc sine of root 3 over 2. Okay, so we're looking for theta. And the thing that we know about theta is that sine of theta should be equal to root 3 over 2. Okay, so I'm rewriting this, like I'm basically converting from this equation to this equation, right? I'm rewriting this where I have this variable theta that I'm trying to solve for, and I have it now represented in this basic trig equation, which we've dealt with before. Okay, so now the question is, which angle, and specifically between negative pi over 2 and pi over 2, is going to give us an output of root 3 over 2. So I'm actually going to write this out because this is sort of like the script that I go through in my head. So the question, which angle theta between negative pi over 2 and positive pi over 2 gives us, you know, root 3 over 2 as the sine value. Okay, I'm going to think about the unit circle here. And since we're looking between negative pi over 2 and positive pi over 2, this is going to give sort of like a restricted portion of the unit circle. This is actually the right half of the unit circle. So let me draw out the right half of the unit circle. I'm just going to do that right here. Right half the unit circle. Okay, there we go. Okay, and now I'm trying to find some angle where the sine, which, you know, that would be the y coordinate, is going to give me root 3 over 2. Okay, so right here, I'm thinking about this angle. Root 3 over 2 is actually a familiar value, because I know that this ordered pair right here, you know, this is the ordered pair 1/2 root 3 over 2. This comes from this angle, theta. That angle theta is pi over 3. Okay, and it turns out that's the only value, that's the only theta value that's going to give me a y coordinate of root 3 over 2, right? There is another one over here, you know, like 2 pi over 3 also would give me, you know, sine of 2 pi over 3 is also root 3 over 2. But the whole point of restricting this to the right half of the unit circle is I only want a single output value, right? If I got more than one output, then I wouldn't have a one-to-one function. I wouldn't be able to, you know, evaluate this arcsine function. Okay, so that is going to be the angle that I want. So I'll say, so theta is equal to pi over 3. Thus, arcsine of root 3 over 2 is equal to pi over 3. And I'll box that up as my answer. All right, so our procedure here is just set up the basic trig equation involving just the sine function, where we're trying to solve for the angle theta, look to the right half of the unit circle and find the theta value that gives us that y coordinate of whatever the value is, in this case, root 3 over 2. Let's try part B. This time we're looking for sine inverse of negative root 3 over 2. So we just saw root 3 over 2. Now we're just looking at negative root 3 over 2. Again, I'm going to start by saying, let's let theta equal sine inverse negative root 3 over 2. So that means that sine of theta is equal to negative root 3 over 2. A little easier to think about if I have this equation. And I'm going to do the same thing, same strategy. Let's look at the right half of the unit circle. I'll draw it in here. And I'm thinking, okay, where do I have a y coordinate? Again, y coordinate because we're looking at sine here. Sine is always the y coordinate of the terminal point on the unit circle of negative root 3 over 2. So down here I have this ordered pair 1/2 negative root 3 over 2. So there it is, y coordinate is negative root 3 over 2. And I'm just asking myself now, what is this angle? What is this angle down here that gives me this? This is going to be negative pi over 3 this time. Okay, this angle right here, theta, is negative pi over 3. The main difference here is, this value, this output value is less than 0 compared to the previous example where the output value was greater than 0. Okay, so, you could think about this like all students take calculus, right? Everything is positive down here. All students take calculus. Down here, this is where cosine is positive, but sine is going to be negative, right? And we have a negative sine value here. So that's why we find ourselves in the fourth quadrant. So that tells me, so theta then must be equal to negative pi over 3. Thus, sine inverse of negative root 3 over 2 is going to be equal to negative pi over 3. Okay, we've got one more here. What about arc sine of negative 1? Okay, well again, I want to set this up. Let's let theta equal arc sine of negative 1. So then sine of theta is equal to negative 1. It's just easier to think about it this way. Now I'm thinking, where on the unit circle, on the right half of the unit circle specifically, between negative pi over 2 and pi over 2. Yeah, just to clarify that real quick. This angle down here is negative pi over 2, right? And this angle up here is positive pi over 2. Just to clarify why we're looking at the right half of the unit circle, given that the range of our inverse sine function is between negative pi over 2 and positive pi over 2. Okay, so let's go over here and look again at the right half. Now, what terminal point gives us a y coordinate of negative 1? Well, down here, that is the ordered pair 0, negative 1. So what angle is this? Right, so there's our initial side at the positive x-axis, and then we have our terminal side down here at the negative y-axis. So this is the angle theta. And this is actually a right angle. So we can see theta, in this case, is going to be equal to negative pi over 2. Okay, so it's actually on the far end. So if we're looking at the graphs of these two functions, we are over here. Okay, just looking at the graph of arc sine of x, that's the ordered pair negative 1, negative pi over 2. Okay, so we ended up with that point in this problem. So theta is equal to negative pi over 2. Thus, that means that arc sine of negative 1 is going to be equal to that angle we found, negative pi over 2. All right, so that's our procedure for evaluating inverse sine functions at given values. Look to the right half of the unit circle. Now, what about arc cosine functions? Oh, a little typo here. That should just be one S there. So recall that y equals cosine of x also has a range from negative 1 to positive 1. and it's also not one-to-one. So we're going to have to restrict the domain again. Now, what happens if, in order to try and attain this inverse, this arc cosine function, what if I used negative pi over 2 to pi over 2, just like we did for the sine function? Turns out we run into an issue. This does not pass the horizontal line test. Okay, this is not one-to-one. This is not a restriction of the domain that makes cosine one-to-one. So I'm not going to do that. The strategy that we used for sine was, pick an interval between a peak and a trough, or between a trough and a peak, so that we cover that entire range from -1 to +1, and we don't fail the horizontal line test. So this time, let's restrict the domain. How about from 0 to pi? I think that's going to work better. Okay, we're going to do that instead. So let's restrict the domain to, this time, 0 to pi. Okay, and once we do that, then we can define an inverse cosine function, and it's going to look like this. Okay, and again, we could pick out some sort of familiar ordered pairs here, like, how about that ordered pair? That is the ordered pair, so the input is √2 over 2, and the output is pi over 4. All right, and this is because, I won't write it all out, but like we were looking at with sine, like cosine of pi over 4 is √2 over 2. Therefore, cosine inverse of √2 over 2 is pi over 4. Okay, and the definition of the arc cosine function looks very similar to what we were just talking about with sine. The big difference to remember is that now the range of the arc cosine function is between 0 and pi. So rather than looking at the right half of the unit circle, what part of the unit circle is this? From 0 to pi, what part of the unit circle are we going to be working with here? This is actually the top half. Okay, so when we go to solve trig equations or evaluate inverse cosine functions, we're going to be looking at the top half of the unit circle. So let's try example 2. We've got a couple problems here. Let's start with arc cosine of 1/2. So I'm going to use the same strategy. Let's let theta equal arc cosine of 1 over 2. Right, so then cosine of theta is going to be equal to 1/2. And note, it's very important, this angle theta that we're looking for is going to be somewhere between 0 and pi. All right, so let's look at the top half of the unit circle. So I'll sketch it in. Now, where in the top half of the unit circle do I have an x-coordinate, right? X-coordinate because the output of the cosine function is the x-coordinate of the terminal point. Yeah, where do we get an x-coordinate of positive 1/2? That's going to be right here, right? The x-coordinate, whoops, sorry, I drew that a little too far over. So right about here, right, there's 1/2. Remember, this is 1 because this is the unit circle. So the x-coordinate is 1/2. And the y-coordinate is √3 over 2. Okay, and I know that just from memory. And now I have to think, what is this angle here? which has that terminal point, 1/2 root 3 over 2. That is theta equals pi over 3. Okay, so then that means that arc cosine of 1/2 is going to be equal to pi over 3. All right, the output of the inverse function is the angle. Okay, great. Let's try the next one. Cosine inverse of negative root 2 over 2. So whenever I see root 2 over 2, I'm kind of already thinking like, okay, this is, I think, either going to be pi over 4 or maybe the other one, which would be in the top half of the unit circle, would be 3 pi over 4. Right, so just whenever I see root 2 over 2 or negative root 2 over 2, I know it's going to be one of those. Let's see which it is. I'm just going to jump straight to the, drawing the unit circle here. As you get more experienced, you might find that you could evaluate these a little more quickly. Where do I have an x coordinate, since we're looking at cosine? Where do I have an x coordinate of negative root 2 over 2? That's going to be on this side of the y-axis. It's going to be in the second quadrant, right? And the ordered pair is negative root 2 over 2, root 2 over 2, like that. Okay, so you could just recognize that the x coordinate is negative, so it's going to be in quadrant 2. Or you could think, all students take calculus, since it's going to be either here in A or S. Since it's negative, it's going to have to be in that second quadrant there. But yeah, and then here's our angle theta, which ends up being, in this case, 3 pi over 4. Okay. So I'll just put my answer here. Cosine inverse of negative root 2 over 2 is equal to 3 pi over 4. Okay, and then one more. What about arc cosine of negative 1? Just draw out my unit circle. I'll do this one real quick. Where do I have an x coordinate of negative 1? Right there. Okay, what angle is that? That is pi. Okay, so in this case, theta is equal to pi. Okay, so arc cos of negative 1 is going to be equal to pi. Okay, very good. I wanted to mention that there is like a cosine inverse and a sine inverse button on your calculator, assuming you have, a scientific calculator or a graphing calculator. There will be a little button. Usually you have to hit second, right? So on your calculator, you can find like cosine inverse of negative 1. Like if you wanted to check your work for this last example we just did, what you have to do is you hit the second button. So it's like you hit second, and then you hit the cosine of x button. And what you'll see is when you hit the shift key, the second button, right above cosine of x, it'll say cosine inverse, or maybe it'll say arc cosine. And then you'll just type in negative 1 as your input. And then you should get an output of, it's going to give you, most likely, unless you have a fancy new calculator, it's probably going to give you an output of 3.1415 something something something. That is just pi. If you get a number that is different from this, you might get it in terms of degrees. Okay, so also it's possible that you would get an output of 180 degrees, so 180. But we tend to want to do these problems in terms of radians. Okay, because radians are just like real number output values. For most intents and purposes, we want to use radians. Okay, so I'll just say radian mode. If you're ever trying to evaluate trig functions or inverse trig functions on your calculator and you're getting confused by the outputs, check whether you're in radian or degree mode. Okay, I think that's enough for now for just evaluating inverse sine and cosine functions. Here are these cool little applications that we can do, these little kind of puzzle problems. So for example 3, we want to evaluate a couple of these. First, we want to find tangent of cosine inverse of 1/3. So this is kind of scary. You know, we're composing an inverse function with another trig function, and they don't even match. Okay, because if this was cosine of cosine inverse of 1/3, it would just be 1/3 because they would cancel each other out. But here we have a tangent function as the outer function. So how are we going to deal with this? So we'll start just like we did in these previous examples, is like, you know, we'll define theta as being equal to this inverse trig value here. So let's let theta equal cosine inverse of 1/3. So then that means that cosine of theta is equal to 1/3. Okay, so now really what we're trying to find is like, we want to know what is tangent of theta. So we're kind of interested in this theta value here. Here's the tricky part though. This 1/3, like this is not a friendly unit circle value, right? If this was like root 3/2 or something like that, it would be a different story. But 1/3, like I don't know of any angle that has a terminal point with an x coordinate of 1/3. This is just not a nice number for the unit circle. So what we're going to do is we're going to use a trick. Okay, so here is the trick. We're going to use the Pythagorean identity to find sine of theta, and then tangent of theta will just be sine of theta over cosine of theta. Oops, cosine of theta. Okay, so that's the trick that we're going to use here. Okay, and we're also going to have to use all students take calculus. I'll mention that when we need it. So the Pythagorean identity, how are okay, so first of all, we have a few different Pythagorean identities. Let me quickly jump up. Oh God, when is the last time that we see this? Oh, I guess it's actually in the previous section. We have a few of them. We have sine squared plus cosine squared equals 1. We have, what's the other one? 1 plus cotangent squared equals cosecant squared. You know, like we have a few of these. I'm not going to write them all out. So which will we use in order to, you know, find this sine of theta? So first of all, you know, we have cosine. We know what cosine is. So that kind of tells us it's going to be the one that involves cosine, which would be this. Sine squared theta plus cosine squared theta is equal to 1. Okay? So I'm going to substitute in the value that I have, sine squared theta, in for cosine of theta. So I'm going to put in 1/3 squared, and that'll be equal to 1, like that. Okay, so sine squared theta plus 1/9, that's what I get when I square that, is equal to 1. So sine squared theta is going to be equal to 1 minus 1/9, which gives me 8/9, like that. And to finish solving for sine, I'm going to take the square root of both sides, and I'll get that sine of theta equals plus or minus, right? Whenever we take a square root, it's plus or minus the square root of 8/9. Square root of 9 is just 3, so I could just put a 3 on the denominator. Square root of 8, that simplifies to 2√2. Okay, so now there's the question of like, wait, we got a plus or minus, like which is it, plus or minus? This is when we're going to look back and think about, okay, so we're looking for sine of theta. What do we know about theta? Well, notice up here, cosine of theta is equal to 1/3. Okay, so since 1/3 is greater than 0, cosine is positive, right? So thinking about all students take calculus. So let me just draw a little one of these things. All students take calculus. So theta is going to be some value in the first two quadrants, right? Because this is coming from an inverse cosine. And since it's positive, that tells us that it's going to be in the first quadrant. Okay? So theta is in quadrant 1. So is sine going to be equal to positive or negative 2√2/3? It's going to be positive. Okay, and maybe I'll label this with a different color, green. And I'll just say positive since theta is in quadrant 1. Okay, so in order to determine if it's positive or negative, we have to look back to this step in the problem where we define this theta, and we can figure out which quadrant the angle theta is in. Okay, so kind of a lot goes into that, but that's where that comes from. Okay, so now I can take this. So now tangent of theta is going to be equal to sine of theta over cosine of theta. I wish I put a little more room for us on this problem. Sorry about that. Sine of theta is 2√2/3, and then divide by cosine of theta, which is 1/3. To divide by 1/3, which is the same as times 1/3, I get 2√2 as my answer. Okay, so these ones are difficult. They involve using the Pythagorean identity to try and figure out what what the output of this is going to be. Okay, we'll do one more, and then we have another one a little farther down the page. But let's try this one. Cosine of sine inverse of negative 1/6. So I'm going to start the way I'd pretty much always do with these. Let's let theta equal the inverse trig function. So sine inverse negative 1/6. So then that means that sine of theta is equal to negative 1/6. Okay, now for this one, we actually have a negative value in here. Okay, so when it comes to the all students take calculus, because I'm sort of curious, like, which quadrant is theta going to be in? All right, all students take calculus. Well, I know that it's going to be on the right half of the unit circle because I'm looking at an inverse sign here. Right, and the outputs of this are always going to be in the right half of the unit circle. Since this is negative, it's not going to be in quadrant 1 because otherwise sine would be positive. So that tells me that theta is in quadrant 4. Okay, so I'll just make a little note of that. Note, since negative 1/6 is less than 0, that means that theta is in quadrant 4. All right, so that will be important when we go to determine if we have a plus or minus, because that's going to happen again. All right, let's use the Pythagorean identity again. This time we're trying to find cosine of theta. Right, this is just equal to cosine of theta because theta is what we defined, or we defined theta to be that input sine inverse of negative 1/6. So let's do it. We're going to use the Pythagorean ID, and we'll use the sine and cosine one again. So sine squared theta plus cosine squared theta is equal to 1. And in for sine, I'll put negative 1/6. All right. Okay, and solving for cosine squared, so I'll get cosine, oh sorry, this should have been squared, negative 1/6 squared. This is going to be 1 minus negative 1/6 squared. I actually get 1/36, like that. So cosine squared theta is equal to, I could get common denominators. I get 35 divided by 36. And then I'll take the square root of both sides. And there will be a plus or minus in the next step. So cosine of theta equals plus or minus root 35/36, or I could just write that as root 35/6 because root 36 is a perfect square. Is it going to be a positive or a negative value though? Well, we're in quadrant 4 and cosine is positive in quadrant 4, so this is going to be a positive value. Okay, and I can just say down here, positive, since theta is in quadrant 4. Right? Remember, all students take calculus. Okay, and we're almost done. Or no, we actually are done. So just to write out everything that happened here, we were trying to find cosine of sine inverse of negative 1/6, right? And then we defined sine inverse of negative 1/6 as theta, and then we just solved for cosine of theta, which we found was positive root 35/6. So I'll put a box around that. Now example 4, it looks kind of similar, but we have a variable x in here, right? So sine of cosine inverse of x, and we're asked to write this as an algebraic expression in terms of x. The process is going to look very similar. Let's let let's let theta equal cosine inverse. It's just always easier to be oriented this way, where we know cosine inverse is some unknown angle theta. So then that means that cosine of theta is equal to x. And now let's go to the Pythagorean identity. We get sine squared theta plus cosine squared theta is equal to 1. This is something that we should have memorized by now probably. And we know, so okay, sine squared theta, and then I can substitute in for cosine x, so this is going to be x squared, is equal to 1. Okay, and what I'm trying to do here now with this is I want to solve for sine theta just like I did in the previous examples, because ultimately what I'm trying to represent here is sine of theta. So I'll solve for sine theta, and what I end up with is this, plus or minus the square root of 1 minus x squared. I kind of skipped over the steps there, but you can totally do that on your own. Okay, so now with this means that sine of cosine inverse of x, we define cosine inverse of x as theta, and I just solved for theta, and I got plus or minus, or sorry, sine of theta, I got plus or minus square root of 1 minus x squared. Now, which is it, plus or minus? I'm going to add a little note here, so I'll say note. If, we're given that cosine inverse of x was in, say, the first quadrant, then sine of theta would be positive. So we would have, positive square root of 1 minus x squared. Right? And then the other case is like if cosine inverse of x was in, so what's the other possibility? It could be in quadrant 1 or it could be in quadrant 2. Right? Because remember, cosine inverse, the output's going to be in the top half of the unit circle, so between 0 and pi. So that's the other possibility. Then, again thinking all students take calculus, what's going to happen to sine of theta? In this region? Well, in quadrant 2, it's also positive, right? Because S, right? So all are positive here, sine is positive here. So it's also going to be positive in this region. So that means that we can just erase this in our answer. This is just going to be positive. Okay, so again, starting by letting theta be whatever our inverse trig function is, using the Pythagorean identity, and then this trick here of determining whether this is positive or negative by just looking at all students take calculus and what the possibilities are for theta, and we find that it's positive in any case. So that's why our answer is positive square root 1 minus x squared. Now we have one more inverse trig function to define, arctangent. We're not going to deal with arc cosecant, arc secant, arc cotangent right now. We're going to stop at this one, but let's check it out. So this is all going to be very familiar. We're going to restrict the domain of the tangent function, this time from negative pi over 2 to positive pi over 2. So this is going to be similar to sine. We're going to define it as, the outputs of the arctangent function as being on the right half of the unit circle. So I'll just make a note that our range in this case comes from the right half of the unit circle. Similar to sine. Okay, so restricting our domain, in this case to negative pi over 2 to positive pi over 2, we get this kind of shape, which notice that the range of tangent in this area is negative infinity to positive infinity. Okay, we're used to dealing with a range of a trig function or the domain of the inverse as being negative 1 to positive 1. So we actually have an infinite, all real numbers is going to be the domain for our arctangent function. And graphed, here it is. Okay, so let's try and evaluate a couple of these problems. Example 5. Part A, we have tangent inverse of 1. Let's start by defining theta. Let's let theta equal tangent inverse of 1. So then, of course, that means that tangent of theta is equal to 1. Now, what this means is, if we wanted, we could break up tangent as sine of theta over cosine of theta. Okay, and if sine of theta over cosine theta equals 1, this means that sine of theta is equal to cosine of theta. So where do we have, in the right half of the unit circle, the x and y coordinate of the terminal points are equal to each other? That's one way that we can think about this. Okay, but ultimately we're trying to answer the same question that we are with those other inverse trig functions. It's like, what angle between, in this case, negative pi over 2 and pi over 2 gives, tangent of theta equal to 1. So drawing my unit circle, it's going to be somewhere on the right half of the unit circle. So yeah, again, back to this thing, like, where are sine and cosine going to be equal to each other? That's kind of a little bit of a trick for this one. And I know that they're equal to each other right here, right? Because this is the ordered pair root 2 over 2, root 2 over 2. And the angle that's associated with that terminal point is pi over 4. Okay, so I can say, so theta is equal to pi over 4. Okay, so then that means that tan inverse of 1 is going to be equal to pi over 4. Okay, you also could have looked at this and thought about right triangles. Some people prefer thinking about right triangles, maybe especially for tangent. For tangent, remember, like if that's our angle theta, here's opposite, here's adjacent, here's hypotenuse. Remember, tangent is opposite over adjacent, right? So you also could have thought, like, for what angle theta do we have opposite over adjacent equal to each other? Well, that would just mean that these two sides are congruent. You know, this would be an isosceles right triangle. This is a 45, 45, 90 triangle. So you could have come up with it that way as well. You know, 45 degrees being the same as pi over 4. So just another approach to that same problem. But I hope you see this is very much the same kind of procedure that we are doing when working with sine inverse and cosine inverse. Now for part B, we have another one of these, sine of arctan of negative 5 over 3. And now seeing that we have a, you know, an arctangent inside of a sine, one of these composition problems, I'm thinking this is going to head towards using a Pythagorean identity to help solve this. But, you know, I'll start like we usually do, where I will let theta equal arctan of negative 5 over 3. All right, which means that tangent of theta will be equal to negative 5 over 3. All right, and thinking about, you know, what the solution theta, like where this might be, notice that this output here, negative 5/3, this is less than 0. Okay, so thinking about like where this angle might fall in the unit circle, just to get ahead of that. For tangent inverse, we're always thinking about the right half of the unit circle, just like we do for sine inverse. And, you know, so our output is either going to be in quadrant 1 or in quadrant 4. All right, and remember we have all students take calculus. So since this is a negative value here, right, negative 5/3, tangent of theta is negative either in, let's see, you know, the second quadrant or the fourth quadrant, right? So that means that this value of theta is going to be in the fourth quadrant. Okay, if this was a positive 5 over 3, you know, we know that it's somewhere in the right half of the unit circle. So if it was a positive value, it would have to be up here in all, because, you know, this is where all of the trig functions are positive down here. This is where only cosine is positive. So sine and tangent are both negative down here. Okay, so we know that our value is going to be in the fourth quadrant, or our theta, that is. Okay, let's keep going now. So now that we have theta is arctan, really we're just trying to find what is sine of theta. Okay, this is where we're going to jump to a Pythagorean identity. So and remember, in the previous examples we used sine squared plus cosine squared equals 1. And we used that in the past because we knew we had some value for either cosine or for sine. In this problem, we have a value, negative 5/3, for tangent of theta. So rather than using sine squared theta plus cosine squared theta equals 1, I might use one of our alternate Pythagorean identities. I'm thinking of this one. Tangent squared theta plus 1 is equal to secant squared theta. Okay, and remember, we can derive this from the original sine squared plus cosine squared equals 1 by dividing both sides of the equation by cosine squared theta. Or you could just memorize this. Okay, so I know that tangent is equal to negative 5/3, so let me make that substitution. In here we're going to have negative 5/3 squared plus 1 should be equal to secant squared theta. Okay, so that gives me, when I square this, I get 25 over 9. Positive, because I squared the negative. Okay, and then, adding these together, I could express that 1 as 9 over 9. Add those together and I get 34 over 9 is equal to secant squared theta. And this is where I take the square root of both sides. Remember, I'm trying to find sine of theta. So I see that I'm getting closer to having secant of theta, which isn't quite what I want, but I'm just kind of pursuing this and seeing if I can come up with sine somehow from this. So let's just see where this takes us. I am left with plus or minus the square root of 34 over 9. 9 is a perfect square. I'll just write this as root 34 over 3, right? Taking that square root is equal to secant theta. Okay. So now usually we get to this point in these problems where it's like, okay, plus or minus, which is it? Is this going to be a positive or a negative root 34 over 3 for secant? And usually we look to all students take calculus. So secant is 1 over cosine, right? Secant is just 1 over cosine. So if cosine is positive, secant is going to be positive. If cosine is negative, secant is going to be negative. Now, we already determined that this angle theta is going to be in quadrant 4. Sorry, I wrote that. It looks kind of like quadrant 3. This is quadrant 4, like that. Theta is in quadrant 4. All students take calculus tells us that cosine is positive in quadrant 4. Therefore, secant is going to be positive. Okay, so I'm going to make this a positive root 34 over 3, and I'll just include a little note here. I'll say this is positive, so secant theta is positive. Since cosine of theta is positive in quadrant 4, because of all students take calculus. And secant of theta is just equal to 1 over cosine of theta. So they will share their sine, or their sign. Okay, that's good. So we have this now. Now what we want is to find sine of theta. Okay, so let me bring this up here. So what we're trying to find is sine of arctan of negative 5 over 3, right? That's where we started, which is just sine of theta, how we define theta. And okay, so now we have to figure out how can we find sine given that we know what secant is. Well, let's see if we can express sine as some expression in terms of tangent and secant. So off to the side here for a second. Remember, tangent of theta is equal to sine of theta over cosine of theta, right? Notice that we have cosine in the denominator. So another way that we could write this is tangent of theta is equal to sine theta times 1 over cosine theta, which is just secant theta. Okay, divide both sides by secant theta, and we get that, tangent theta over secant theta is equal to sine theta. So that's what I'm going to do over here. I'm going to rewrite sine theta as tangent theta over secant theta. Okay, and now I know that tangent of theta is negative 5/3. Okay. Divided by secant of theta, which is positive root 34 over 3. And we've got this fraction inside of a fraction thing. And this simplifies down to negative 5 over root 34. And if you want to be really good about it, we'll rationalize our denominator. Negative 5 root 34 divided by 34. And that is sine of theta. Okay, so, going from here to here, this is where I used this kind of trick here. There are other ways of doing this. You could have done another, used this over here. And sorry, this is a total mess, but like cosine of theta is just 3 over root 34, taking the reciprocal of secant, which we have. We could have plugged this into another, into another Pythagorean identity. We could have done sine squared theta plus cosine squared theta equals 1 and, substituted this in for cosine and solved for sine. So there are multiple ways that you could do this. This was kind of the path of least resistance for me. But very tricky problem. You have to jump around. You have to be very aware of where your angle is in the unit circle so that you can make the correct, assessment as to what the sign is. So very challenging but interesting problem here. All right, let's move on and talk about some properties of inverse trig functions. So normally, when we take the composition of a function and its inverse, like f of f inverse, it just acts as the identity function for any x value that's in the domain of the inverse function. And similarly, if we have f inverse of f of x, like this, it acts as the identity for any x which is in the domain of f in this case, right? Because f is the interior function. Now the key thing here is that this works for any value of x that is in the domain of f or of f inverse, depending on which is the interior function. And the reason why this is tricky for trig functions and inverse trig functions is, remember, we have to restrict the domain of our trig functions in order to make them one-to-one so that we have inverses. So let's look at this example, and really there's kind of two little examples here. So what if we look at sine inverse of sine of pi over 3? And, the claim here is that it just equals pi over 3. So it sort of acts as it should, take the composition of a function with its inverse, and it just acts as the identity. So let's see why this is. Normally the way we would evaluate this is first we would evaluate the interior function. So what is sine of pi over 3? Well, you could look to the unit circle. Pi over 3 is right here, so what is the y coordinate of that terminal point? I know it to be root 3 over 2. Right, and we're in the first quadrant, so all students take calculus. Since it's in the first quadrant, sine will be positive, so we just get that. Okay, and then what is sine inverse of root 3 over 2? Well, we already kind of have the picture drawn. We just have to make sure that we're pulling values from the right half of the unit circle. Right? And root 3 over 2, what we're going to output is, since we have the terminal point at pi over 3, that has that y coordinate of root 3 over 2, this is just going to be equal to pi over 3. Okay, so we're just sort of verifying that these two values are equal to each other. Okay, and I'll say this works since pi over 3 is in this domain from negative pi over 2 to pi over 2, right? That restricted domain that we use for sine so that we can get an inverse. Okay, but what's going to happen in this next part here where we're looking at sine inverse of sine of 2 pi over 3? The claim is that this is not equal to 2 pi over 3, so it actually doesn't act as the identity function. What happens? Okay, well, let's do what we did a second ago. Let's just start by evaluating what is sine of 2 pi over 3? Well, you could draw your little unit circle. And where is 2 pi over 3 going to put us? It's going to put us in the second quadrant, right about here. Right, there's 2 pi over 3. And then what's the y-coordinate of that terminal point? Well, it's just root 3 over 2. Okay, now what is sine inverse of root 3 over 2? Okay, well, remember, for sine inverse, we are always looking in the right half of the unit circle. We're always looking, our output is going to be somewhere between negative pi over 2 and pi over 2. So our output is actually going to be this angle right here, right? Because this is the angle in that range of sine inverse that has a terminal point y-coordinate of root 3 over 2. So this is actually going to output pi over 3. Okay, so notice that this is not equal to what we might have expected just based on that basic principle of trig function or of inverse functions. Okay, so I'll just put another little note over here. So I'll say note sine inverse of sine of 2 pi over 3 is actually equal to pi over 3. And this is because 2 pi over 3 is not in the range of sine inverse. Okay, remember that restricted range is negative pi over 2 to pi over 2. Okay, so something to be careful of. We have to be careful when we're dealing with compositions of trig functions with their inverses. Okay, and then here just all the rules sort of spelled out. If we have arcsine of sine of x, like this property is only going to work. It's only going to give us the identity function if we take the composition if x is in that restricted domain from negative pi over 2 to pi over 2. Okay, and then if it's the other way around, sine of arcsine of x, this will be the identity function for x between negative 1 and positive 1. Okay, and then looking at arc cosine of cosine, again, we run into this kind of tricky thing where we have to be careful. This only is going to be the identity function for those values of x that are in the restricted domain of cosine, right? So this is 0 to pi. This is the restricted domain of cosine x. Okay, same thing for tangent. It's only going to be the identity function on that restricted domain, negative pi over 2 to pi over 2, and so on. So let's try a couple of these. We want to evaluate the following. So part A, example 7, part A, we want cosine inverse of cosine of pi over 8. So before I start going through the process of first evaluating this and then evaluating that and, doing a bunch of work, I can just think, hey, if pi over 8 is in the restricted domain of cosine, or in other words, if it's in the range of cosine inverse, this is just going to output pi over 8. So it turns out that is what happens in this case. This is going to be just equal to pi over 8. And I'm able to do this because pi over 8 is in the restricted domain from 0 to pi. Okay, so it's in the range of cosine inverse. Okay, cool, easy. Let's move on. What about sine of sine inverse of 1/5? Now for these, if we have, sine on the outside and the inverse function on the inside, we're just wanting to make sure, is this value 1/5? Is it between -1 and +1? In this case, it is. So this is just going to be equal to 1/5. Okay, and again, I'll provide the little justification here. This is because 1/5 is in this range of -1 to +1. Okay, so that cancellation property, the identity property, applies. Now what about this one? Cosine inverse of cosine of 5 pi over 4. Okay, so this one I'm a little suspicious of. So notice that 5 pi over 4, this is greater than pi. Okay, so 5 pi over 4 is not in this set, so that symbol is just not an element of that restricted domain of cosine from 0 to pi. So what this means is we're going to have to do this one step at a time, which is no big deal. We can handle it. We're going to do this one step at a time. First, let's evaluate cosine of 5 pi over 4. So thinking about, we could do the reference angle thing. Okay, so if theta equals 5 pi over 4, theta prime is going to be the reference angle. We can draw a little picture here. Five pi over 4, that is down here. Right, and you could count that 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then 5 pi over 4 is where we land in the end. Okay, and with that we could figure out what our reference angle, it's just going to be this shortest angle right here, dropping down to the negative x-axis. That is just pi over 4. Okay, so what is cosine of pi over 4? Well, that's just going to be positive root 2 over 2, right? So we know that this is going to be either positive or negative root 2 over 2 going in here. Which is it? Well, all students take calculus. So down here in quadrant 3, tangent is positive, but sine and cosine are both negative. So this is actually going to be negative root 2 over 2. All right, so we evaluated cosine of 5 pi over 4 using reference angles. Now, what is cosine inverse of negative root 2 over 2? Cosine of what angle? So we're thinking cosine of what angle theta is equal to negative root 2 over 2. And we are looking in the top half of the unit circle, remember, between 0 and 2 pi. So which angle in this region has a terminal point with an x-coordinate of negative root 2 over 2? That's going to be right here. And that angle is 3 pi over 4. And I will box that up. Okay, so again, sometimes if we have a value like this, 5 pi over 4, that doesn't fall in that domain from 0 to pi. We got to be careful, work through this, and we might get an answer. And we'll see that in this case, it doesn't follow that property where it always equals the identity function if you take the composition of a cosine inverse function and a cosine function. Okay, let's keep going. There was a misplaced problem right here, so I had to take that out. The last problem of this section and of this chapter, actually, example 8, a 5-mile straight segment of road climbs a 4,000-foot hill. Determine the angle that the road makes with the horizontal. Okay, so a little application problem here. I'm expecting some kind of right triangle to pop up. We have a road that's going up a hill, and this 4,000 feet, that's like the height or the elevation climb of this hill. So let me draw a little picture. I'll draw a little picture over here. Let's say here's the hill that we're going up. Okay, and if we're talking about the height or the elevation, we're sort of talking about the distance from the horizontal, maybe at the start of this 5-mile stretch. So the triangle that I see sort of coming together here is, we have this height, which is 4,000 feet. And we have this stretch, of road that we're actually driving on. This is 5 miles. The first obstacle that I'm seeing here is that we have different units, right, for the road and for the height of the hill, miles and feet. So ideally we want to get this all in terms of, the same units. And there's this fact. So note that 1 mile is equal to 5,280 feet. Okay, this is going to be relevant so that we can get everything either in terms of miles or in terms of feet. If something like this were to appear on a quiz or a test, I would give you this conversion, okay? So what do I want to do? Do I want to go into miles or into feet? I think that I'll probably want to go into feet, because if I convert this into miles, that's going to be less than 1 mile. I'm going to end up with a decimal there. I think I'm going to try to avoid that. Let's convert this 5 miles into feet instead. So I'll say first, let's convert 5 miles into feet. And here's how we do this. So we have 5 miles, and whenever we have something like this, we can create a conversion factor. And in this case, I want to convert from miles into feet. So I'm going to create a big 1, and I'm going to express this like this. 5,280 feet divided by 1 mile. And since those two values are actually representing the same distance, this is just a big 1. So I can multiply those straight across. So that means that 5 miles, I'll just multiply 5 times 5,280, and I get this number, 26,400. And the miles cancel out, and we're just left with feet. Okay, so I might update my triangle and just write that side length as actually 26,400 feet. Okay, good. Now, what am I actually asked to do here? I want to determine the angle that the road makes with the horizontal being that line right there. So I'm trying to find this angle, and I'll just call that theta. How about? Okay, so the next step here, so now we want to find that angle theta. Okay, so here's how we're going to do this. We can set up a basic trig equation involving that angle theta and the two known side lengths that we have for this triangle, which relative to theta are the opposite side and the hypotenuse. So which of our 6 trig functions relate opposite and hypotenuse? I think that's going to be sine, right? So we have that sine of theta is equal to opposite over hypotenuse, which will be 4,000 divided by 26,400. Now this value 4,000 over 26,400, this is not some y coordinate that I recognize on the unit circle, right? This is not an easy value to deal with. If this was like 1/2 or root 3 over 2 or something like that, maybe I'd be drawing unit circle, but that is not going to work for us this time. I'm going to convert this equation and I'm going to rewrite it using sine inverse. So remember, I can convert this and I could express it where theta is isolated, and theta will be equal to sine inverse of 4,000 divided by 26,400. And I can enter this into my calculator using the sine inverse function. So let me jump over to my calculator for a second and show you how I'm going to do this. Okay, here we are. So before anything, I want to decide, do I want my calculator to be in radian mode or degree mode? And either will really work here. I think given the application problem, generally when we're talking about angles of elevation and stuff like that, it's common for the answers to come in terms of degrees. I would accept either in this case, but I'm going to click on mode and I'll go down, down, and put this into degree mode. So I'll just highlight degree and hit enter. And now we're in degree mode. And I can do second, quit, and now we're ready to type in our problem. So remember, we are trying to find sine inverse of, this unsimplified fraction, 4,000 over 26,400. So sine inverse, you'll see this button down here. I don't know if you can see my cursor very lightly down there, but the sine button up in blue, we can see it says sine inverse. So to hit sine inverse, we have to hit second, that shift key, and then the sine button, and we get sine inverse like that. And I could just type in my fraction here. I'm not going to put in the effort of simplifying this fraction since it's just going right into my calculator. 4,000 divided by 26,400, and close the parentheses, check, make sure I typed everything in correctly. That looks okay. I'll hit enter. And here is the angle that I get. Remember, this is in terms of degrees, so 8.7147 something something. I think I'll just round this to the nearest hundredth of a degree. I think that's plenty precise for us, for our purposes. So I'm going to provide my answer as 8.71. All right, from my calculator, I got that theta is equal to 8.71 degrees, and really this is an approximation, so I'll put approximately 8.71 degrees. So that's going to be our final answer for this. We wanted to determine the angle that the road makes with the horizontal, and we can just box this up. Okay, in the case that you wanted to convert this to radians, you could totally do that by multiplying it by that conversion factor. If we wanted to go into radians, we could multiply 8.71 degrees by this big one, which is going to involve 180 degrees and pi radians. If we're trying to cancel out the degrees, the 180 degrees would go down here, and then pi would go up top, and you could multiply straight across and get your answer in terms of radians. Okay, So if I don't specify in a problem, like I don't in this one, I'm happy with either of those answers. But that brings us to the end of this section on inverse trig functions. It's a pretty heavy one. It takes a lot of practice getting used to. Take your time on your homework, use your notes, let me know if there are questions, and then we'll pick things back up in Chapter 9.